14.
Good morning, everybody. So let us now talk about the Bernoulli's law of large numbers. Last time we have done with the Bernoulli's random variables. We have tried to calculate the mean of Bernoulli's random variable and the variance also. Then if you repeat the Bernoulli's trials, then you lead to binomial distribution. So we also calculated in our previous lecture the mean of the binomial distribution and the variance of the binomial distributions. The mean was equal to NP. What is N? N is the number of trials. And what is P? P is the probability of success. And about the variance of the binomial distribution, it came out to be NPQ. Number of trials into probability of success, Q is the probability of failure. So that is the variance that you will get in the case of binomial distribution. All right. Actually, this mean value and the mean value, which is NP, and the variance is needed to prove what is the Bernoulli's theorem, which is actually very famously known as law of large numbers, right? And I also explained you the intuitive meaning of the law of large numbers. I will once again very quickly go through the intuitive meaning, and then we will discuss about the mathematical background and the proof of this theorem. Let me just come back to, if it is there in my presentation, let me check actually. Sure, it is there in this. Yes, it is there. Let me go with the full screen mode. Okay. Yes, this was my law of large numbers. Let me come to only, I will discuss the no, I think it's not there. It was there in the previous slides. Okay, but I will just tell you the meaning of the law of large, the intuitive meaning of the law of large numbers. So what do you mean by the law of large numbers? What does it actually say? It says that you have a number, let us say you perform an experiment. And I'm again and again taking the example of a very famous experiment of explaining the things is the tossing of a coin. So you get two outcomes, heads and tails. All right. So the probability, the theoretical probability associated with getting the head is half and getting the tail is also half. You can calculate the expected value from the theoretical probability. For example, if I designate head as 0 and tails as 1, so 0 into half plus 1 into half, that will be my expected value. That means that is my theoretical probability, and it comes out to be 0.5. But in the case of when you really perform the experiment, for example, you toss the coin 100 times, and it may not be possible that you get 50-50, 50 times head and 50 times tail. You may end up with 45 times heads and 55 times as tails, or 46 times as heads, 54 times as tails, right? So that we call and if there are, let us say, first time, so expectedly when you toss the coin 100 times, theoretically you must get 50 times heads and 50 times tails. So that is my theoretical expected value. That we call as the expected value, or we also call this as the mean. But there is one more term which is known as sample mean. So what is the meaning of sample mean? When I take my first 100 trials, right? Let us say I get 45 times heads and 45 times tails. So next time again I perform the again I toss the coin 100 times. I may end up with 52 times heads and 48 times tails. But if I look at the probability of the heads, and if I try to get the mean value, what is mean? What mean I am trying to calculate here is that for my first 100 tossing of the coins, I end up with, let's say, 45. For the next 100 tossings of the coin, I end up with, let's say, 55. For the third 100 tossings, let's say, end up with 52 heads. All right. Then if I calculate the mean of this repeated experiments, that will be called as the sample mean. Today, I will also briefly discuss the central limit theorem, and I will take up this issue of sample mean once again. Probably I have made it very clear the difference between the sample mean and the expected value or simple mean, right? What the law of large numbers says, it says that when the number of trials, that means n, goes towards infinity, the sample mean approaches towards the expected value. That means for 1 or 2 experiments, you may end up with 45 heads or 50 heads or 40 heads or 60 heads. But eventually, when n becomes very large, your sample mean will approach towards the expected mean or the expected value. So that's the law of large numbers intuitively. But let us look now this law of large numbers in more analytical and mathematical terms, that how we actually put the law of large numbers in mathematical equations. Now, what does it say? It is also a third question in your tutorial sheet number 2. So consider an experiment with only 2 possible outcomes, success and failure. So that means it is a Bernoulli's experiment. So let P be the probability of success and is assumed to be same for all the trials. N is the total number of trials of the experiment, and xn, I denote it as the number of successes in n trials. Now, what Bernoulli's law of large numbers states that for any epsilon, very small value, it's an error value we are taking. So for any epsilon greater than 0, so the error has to be greater than 0. What it says is that probability of what? Probability of xn, what is xn? Number of successes divided by the total number of trials. That means this xn by n is actually my sample mean. This is my sample mean minus and it is equivalent to the probability, right? So xn by n minus p. What is p? Probability of success. But what is the difference between xn and n? Xn is the sample mean after performing the experiments. What is p? P is my theoretical expected value, which in our tossings of the coin will be 0.5 always. So xn by this theorem says that sample mean minus expected value, the mod of this, when it is less than epsilon, right, will approach towards 1. Will approach towards 1. I will take up the Chebyshev's inequality. There are 2 forms of Chebyshev inequality. In one form, you will get this theorem as approaching towards 1 as n approaches infinity. And in the other form, if you use the other form of Chebyshev inequality, you will find that this approaches to 0 as n approaches to infinity. But I'm proving for when this value approaches to 1 as n approaches to infinity. So let's start the proof. Very quickly we will do. So since xn denotes the number of successes in n trials, that is xn follows a binomial distribution. Why it is following the Bernoulli's distribution? Because the outcomes are 2 only. That means it's a Bernoulli's experiment. And when we are doing the Bernoulli's experiment for more than 1, that means n number of trials, So it becomes a binomial distribution. So our xn is a binomial, is a random variable represented with the binomial distribution with two parameters, n and p. N is the number of trials and p is the probability of success. So xn is a binomial distribution with two parameters, n comma p. And let us find out the expected value of xn, because this is a binomial distribution. So that means what will be the mean of, what will be the expected value of xn will be np. We have proved it last time, and it is given in my notes also. You can check. If you find any difficulty in understanding the maths part of this proof of expected value or the variance, you can always contact me, ask me question. Don't keep any doubts with you. All right. So this is the expected value of a binomial distribution. It comes out to be np. What is the variance of xn? Since again it is a binomial distribution, the variance will be npq. And what is q? Q is equal to 1 minus p. But in the theorem, if you look at the theorem, we are not interested in, or we are not interested only in xn. We are rather interested in xn by n. So let us look at, in the theorem, we are interested in xn by n minus p. Therefore, our variable of interest is xn by n and not this xn. So let us find out the expected value of xn by n, and it can be proved. This is the, I will give in the tute sheet also that how to prove that expected value of ax is, a is some constant. Expected value of ax is equal to a times expected value of x. And variance of ax is given by a square times the variance of x, that means vx. So when we are trying to find out the expected value of xn by n, so here a will be equal to 1 by n. So I can write it to be 1 by n into e of xn. And what is my e of xn? E of xn is np. So when I multiply 1 by n with np, I get p. All right. And what is the variance of xn by n? I know that this is equal to a square vx. What is my a? A is my 1 by n. What is a square? 1 by n square, and this is variance of, and what is variance of xn? It is npq, right? So this will be pq only, not it's not n here. It's not divided by. It is the mistake is here. It is 1 by n square, so it will be pq by n. It is 1 by n square actually. It has to be, but you can make the correction please in your notes also. It is 1 by n square into npq. So 1 n will cancel out and you will get pq by n. So what we have, let's look at the theorem once again. The theorem, in the theorem we are taking xn as the number of successes. It is a binomial distribution. So the mean of this xn is, expected value of xn is np, variance is npq. But we are, as I said, I am interested in xn by n as a variable of interest. So therefore, expected value of xn by n will be equal to p, and expected value of variance, that means the variance of xn by n is equal to pq by n. Now let us look at a standard formula which we call as the Chebyshev's inequality. This is, I can prove this Chebyshev's inequality also, but we will take the Chebyshev's inequality formula straight away and try to prove the, try to look into the law of large numbers. So what does this Chebyshev's inequality states? This inequality discusses a random variable x and its difference from the mean. What does Chebyshev inequality deals with? It deals with a random variable x and its difference from the mean. So it is difference of x from mean mu. Let x be a random variable for which mean mu and variance sigma square exists. Then for this is out of the law of large numbers. I am only at this paragraph only states in general the Chebyshev's inequality, right? So x is a random variable. This Chebyshev's inequality, it has two forms. One is equation number 2, one is equation number 3. Any form can be used. Both forms are Chebyshev's inequality. This theorem says that x minus mu is always great if it is greater than or equal to t sigma, right? So t is any positive number, and sigma square is the variance, sigma is the standard deviation. The probability of what? Probability of mod of x minus mu greater than equal to t sigma will always be less than equal to 1 by t square, right? And what does the other form state? The other form says that probability of x minus mu mod, here you must understand the difference. Here it is greater than equal to, here it is less than equal to. So if this mod of x minus mu is less than equal to t sigma, then the probability is greater than equal to 1 minus t square. But if this x minus mu is greater than equal to t sigma, then it is less than 1 by t square. One theorem, one Chebyshev's inequality will lead to law of large numbers when it will approach to 0. The other will take it to, when n approaches infinity, the other will take it to take the law of large numbers to approach to 1. But so let us continue with our proof of Bernoulli's theorem. What I am doing is that what was my Bernoulli's expression statement? It was xn by minus p less than epsilon. But if I compare this theorem with the Chebyshev's inequality, so what does it say? Comparing equation 1 with equation 3, I'm using this part. I'm not using the first part. I'm using the second part of the Chebyshev's inequality. So it says that xn minus p, right, is less than, here in my statement of the law of large numbers, here it is epsilon, but here it is t sigma. I take t as it is, and I put the value of the standard deviation. We have already calculated the value of the standard deviation. The variance is pq by n. What is the standard deviation? Standard deviation is the under root of pq by n. So I put here under root of pq by n, which is the standard deviation, is greater than equal to 1 minus t square. So that means I'm comparing the statement of the law of large numbers with the Chebyshev inequality, and I am substituting the variables. Okay, so let's continue. So that means t into under root of pq by n is actually epsilon, and I can put it like this: t equal to epsilon divided by under root of pq by n. And what is my t square? It is epsilon square pq by n. So I can take this denominator n on the numerator part. So it will be t square will be equal to n epsilon square pq. Now, if you see the Chebyshev's inequality, it says that this term is greater than equal to 1 minus t square. So when I have calculated t square, so I can put, so xn by n minus p less than epsilon should be greater than equal to 1 minus 1 over sigma square. What is my sigma square? My sigma square in terms of epsilon is n epsilon square divided by pq. So I get n epsilon square by pq, right? I can, the right hand side of the equation, I can put it like this also: 1 minus pq divided by n epsilon square. But now let us say that since the experiment has only two outputs, success or failure, and if the two outcomes are independent outcomes, it is an unbiased experiment. So what is probability of success? It is half. What is probability of failure? It is again half. So assuming the independence, what I will get is, that means I will use p and q as halves. So I use here, it is this probability is equal to 1 minus pq by n epsilon square. So I use the value of p as half, q, the value of q as half. When I use that, I get this equal greater than equal to 1 minus 1 over 4 n epsilon square, right? So what is my law of large number? Basically, it's what it basically says. It says that as n approaches infinity, so when n will approach infinity, of course this term will be 1 over infinity, so therefore it will be equal to 0. So therefore this left hand side is greater than equal to 1, which proves my what I wanted to prove. Actually, I wanted to prove this thing only. let's come to the statement. Yes, this was my statement, xn by n minus p less than epsilon. This probability will approach towards 1 as n approaches infinity. But how I am able to prove this? I am using an inequality, which is Chebyshev's inequality, which is a well-proven inequality. We can have the mathematical proof of the Chebyshev inequality also, but there's no need to go into that detail. But you can straightway take the Chebyshev's inequality and use this inequality to prove the law of large numbers. And while deriving the law of large numbers, we have actually calculated the expected value of this xn, since it is a binomial distribution, though I have calculated this value in my previous lecture, but it is a part of the proof. And we have also calculated the variance of the this random variable xn. It is npq. So when we are using this and we are using the Chebyshev's inequality, we are able to prove that this probability xn by n minus p is less than epsilon, some epsilon value which is very small, will be greater than or equal to 1, and as n approaches to infinity, this right hand side term will be 1 minus infinity, so it will be you can remove the greater part here. Why? Because the probability cannot be greater than 1. So we can very confidently say that the probability xn by n minus p less than epsilon approaches 1 when n approaches infinity. This is my law of large numbers, mathematically proven. But I have already explained you what is the intuitive meaning of the law of large numbers. Please remember that many people, this is a very important law which is used in your computer programming. You take the random number, you generate some numbers, actually your computer uses the law of large numbers, right? And it also uses the central limit theorem, which I'm just going to explain you. What is central limit theorem? But you must understand what is law of large number. The sample mean.
67 billion.
Please mute yourself. Intuitively, the law of large numbers says that the sample mean approaches towards the expected mean when n approaches infinity. This is just if you used. I used the second part of the Chebyshev's inequality, which is equation number 3. But if I use the same type of proof, I would request everybody to please mute yourself, because it is called, excuse me, please mute your microphone. If you use the second part of the Chebyshev's inequality, which is the third equation, but I have used it in my proof. But if you use the equation number 2, which is the other part of the Chebyshev's inequality, then you will lead to value approaching 0.
Hello.
It's becoming very difficult. Somebody is continuously. So this value is approaching to 1 as n approaches to infinity. But if we use the other form of the Chebyshev's inequality, you will find that it will approach to 0 as n approaches infinity, because many books explain it going to be 0 also. So that part has to be kept in mind. I will actually stop sharing this screen. I will share one more screen with you, which actually starts explaining the central limit theorem. So let us look at that.
So we have to learn the whole proof.
Pardon?
So we have to learn the proof of this large probability theorem.
Yes, but what is there? If you just solve it once, you will get it. There is no problem here. See, as far as if you are talking to me in terms of the exam point of view, we will discuss that part later. What is to be done, what is not to be done. But the question here, when I am teaching and you are learning, the question is that you must learn from your heart. That's the point. As far as exams are concerned, I will discuss about the type of, I don't know what type of exam will happen this time, right? Whether online or offline. Let's see how the situation gets for how the things proceed further. But at present, please concentrate on learning. That is very important actually. What I am teaching you is actually the concepts of probability, and you will find that if you will ask many people may not able to tell you what is a random variable, what is probability distribution, what is law of large numbers, what is central Gaussian I'm coming to Gaussian distribution. So these things are very important, and when you try to model a new system. Okay, so learn about the proof, mugging about the proof to write in the exam, we will talk later. All right. Let me share the next screen, please. I hope you will pardon me for the bad quality of the slides. Actually, if I have the written notes, if somebody from you is from Patiala or somebody comes to Patiala, please take my notes and get it scanned once again or get it photocopied from outside. I'm just using my phone camera to scan it, but I have the notes with me. You anytime come to Patiala, please take these notes from me and you can get it photocopied. No problem with that, and then you can circulate further. So if anybody is from Patiala, you can anytime just give me a call and take my notes. All right. So, but I will of course explain. So you will not find in understanding when I'm trying to explain you will not find any problem in the PPT, in the display part. Okay, I will now explain what is central limit theorem. Now, central limit, before going to central limit theorem, let us look at the very, very fundamental part, which will actually take us to central limit theorem. So I'm considering what? I'm considering here any distribution. You can consider any distribution. Right, when I'm writing here, consider any distribution, you can consider any distribution, whether it is Gaussian or not Gaussian or discrete or continuous. You consider any distribution, any probability distribution. And now you will see the power of central limit theorem in the practical life that I'm going to just explain. So what I am considering, for example, here the throwing of a dice. So dice has 6 outcomes, 1, 2, 3, 4, 5, and 6, right? So I'm considering, you can consider any distribution with mean mu and variance sigma square. The point is that the distribution must have some mean and sigma square, which is the variance. All right. So let us draw the distribution hypothetically. Let's say that the dice is little biased. So 1 has this much probability. It is very unlikely that you will get 2, right? Probability of getting 3 and 4 are the same. And it is also very unlikely that you will get 5. And probability of getting 6 is this, as shown. It is when I say that this is a very vague kind of distribution, this nowhere looks like a Gaussian curve or bell-shaped curve. But you will see how you can turn it into the using the central limit theorem like a Gaussian curve. So let's talk about this. This is the probability distribution. All right, let's take samples of this distribution. What do you mean by taking these samples? I take 4, let's say I take 4 samples. Right, and 4 samples I take. Let me come here. I take the sample at outcome 1, again outcome 1, then 3, and then 6. So that means 4 samples I am taking, but actually n is the sample size. What do you mean by the sample size? I take 4 samples. That becomes my S1. That is my first sample actually. When I take 4 samples and I perform the experiment 4 times, that becomes my actual sample. I will call this as actual sample. That means this S1 is actually a set of samples. As my S1 is first set of samples. And what is the sample size? 4. Let's say I'm taking 1, 1, 3, 6. Right? This is my S1. I again repeat the experiment with 4 samples taken from this distribution. Right? And that means I get a set of 4 samples again. I call this as S2. So that means I am getting S1, S2, I will call from now onwards, I will call my S1, which is a set basically. Please remember that. S1 is my first sample. I should call it set of samples, but I'm calling it sample. S1 is my first sample. S2 is my second sample. S3 is my third sample. All right. I'm talking about considering firstly the 3 samples. What is a sample? Sample is basically a set of 4 samples. How this 4 has come? Because I'm fixing my n to be 4. This is my first sample. Then what I do, I take the mean of these samples. This is 1 plus 1, 2 plus 3, 5 plus 6, 11. 11 divided by 4 is 2.75. This is my first sample mean, x1 bar. I hope now you understand the meaning of sample mean. This is my sample mean. This x1, this s1 is my first random variable. All right. Then I also get the mean of the second sample, which is a sample mean of the second sample. It is x2 bar. Again, let's say it comes out to be 2.75. And for the third sample, the mean comes out to be x3 bar comes out to be 3.5. What I have done is I have taken a probability distribution, a biased dice, in which then I am taking 4 samples to create one sample set, and actually I will call that set as sample. In my slide, I'm showing for 3 sets, but if you do it, if you continue doing it for, let's say, 1,000, 10,000, 1 lakh times, but before that, let us concentrate on 3 samples only, and let me explain what I'm trying to say. How many times, and this is my x1 bar, this is my sample mean for the first sample, x2 bar, this is the sample mean of the second sample, x3 bar, this is the sample mean of third sample. In this way, I calculate the sample means. And what I now draw, so x1 bar is 2.75, x2 bar is again 2.75, x3 bar is 3.5. So if I take 10,000, 1 lakh sample, you will get 10,000 or 1 lakh values. Now I want to plot the frequency of occurrences of these means. For example, 2.75 in these 3 samples, 2.75 has occurred 2 times. 3.5 has occurred 1 time. Quite possible 3.3 might have occurred 4th time. Let's take 1.2 might have occurred next time, 5th time, and so on. What I will do is I will plot the frequency of sample means. In the previous slide, I took an experiment of 3 samples. So 2.75 came 1 time, then again it came. So what is the frequency of sample means? The frequency of sample means is 2. And the frequency of sample mean 3.5 is 1. Right? Please understand, I am taking averages and then I am plotting the frequency of sample means. Keep taking samples, thousands, maybe, and so on. Maybe you may go 1 lakh samples. What you will find out? You will find what I'm plotting. Please understand, what I'm plotting is the frequency of sample means. For example, as I'm taking an example to explain, 2.75 came 2 times, 3.5 came 1 time, But if I keep repeating the 10,000, 1 lakh, 2 lakh, 1 million times, what will happen? And what you are plotting frequency of sample means. And you will see that amazingly, this plot turns nicely about normal distribution. So you now try to understand, you started with this distribution. By going like this, where you have ended up? You have ended up with a Gaussian distribution. And as the number of experiments will increase, as it approaches infinity, you will see that it's it's taking the shape of normal distribution. It is approximating to normal distribution. These are the frequency of sample means. All right. Then this is the basic part that I wanted to speak. Then it turns out to be, let's now talk about what is Gaussian distribution. Now, Gaussian distribution is a bell-shaped curve, right? You have X as the, before going to the central limit theorem, let's talk about the Gaussian distribution formula. Though I have I have explained you Gaussian distribution, but let us formally look into what is Gaussian distribution. X, P subscript X, capital X, argument is X. This X is taking values. Capital X is the random variable. It is taking values which we represented through small x, and along y-axis is the probability density. So this is a probability density function of the random variable x. And let's say the probability density function is a bell-shaped curve. And how can you mathematically explain a bell-shaped curve as 1 over, it has mean mu and the variance or the standard deviation sigma. So what is this probability distribution function? This is equal to 1 over under root 2 pi sigma square. Sigma square is the variance. Exponent of minus x minus mu. Mu is the mean, whole square divided by 2 sigma square. This is the formula for the normal distribution or the Gaussian distribution. So it is a bell-shaped curve because the probability density function looks like the shape of the cross section of a bell. So that is why this is very importantly known as the bell-shaped curve, right? Now, equation 1 is the equation for the PDF. Mu and sigma are the variables, and it turns out that mu is the mean of the probability distribution function, and sigma is the, mu actually gives the mean where the peak is occurring. You change the value of mu, your curve will shift to the right or to the left. And what does this sigma tell you? Sigma indicates the width of this curve, right? So if you increase sigma, width will increase. If you decrease sigma, the width will decrease. So you can control the shape of the shape of this Gaussian distribution and the positioning of the distribution through mu and sigma. So you have two points. One is mu and sigma. Mu and sigma are two parameters which actually change the shape of the curve. Right. Then let me not go into the details of this. Now, what is central limit theorem? As I have explained in these slides, and okay, I have changed the, yes. So I was just trying to explain you with this experiment that you take any distribution and you will end up with probability, you will end up with normal distribution. Then I explained what is normal distribution, right? So then now formally let's talk about the central limit. This says that any number of random variables, if they have the same distribution and if you add them up, then the overall distribution will be a Gaussian distribution irrespective of the individual distribution. I will explain this. This is the formal definition of the central limit theorem. But let us look at this part. What does central limit theorem say? It says that if you take random variables x1, x2, xn, compare it with my previous example of throwing of a dice, when I was trying to explain you that a probability distribution, how it takes the shape of a normal distribution. So you take random variables x1, x2 up to xn. If all random variables are taken from same type of distribution, if all random variables we are taking, because as you have seen in my previous slides, I was taking S1, S2, S3, which are sample means. I was getting the sample means from the same distribution, So my S1, S2, if you remember, the previous slides, S1, S2, S3, and so on were taken from the same probability distribution of throwing of a dice. So what I'm trying to say is that if x1, x2, xn are the random variables, and if all the random variables are taken from the same distribution, and if these are independent, of course, in our previous experiment, these were independent. And if they have same mu and sigma square, if you remember, if the distribution is same, of course, the mean of that distribution will be same and sigma square will also be same. So that means any distribution, any shape of the distribution, if you take random variables from the same distribution, and if these are independent, if they have same mean and variance, then what it says that xk, right? Xk is the sample mean. Xk is the sample mean, which I was taking as S1, S2, S3, and so on. So xk is my sample mean, where k is an index which is taking me to S1, S2, S3, and so on. So xk minus mu. What is mu? Mu is the mean of the original distribution. Every distribution will have a mean, right? The sample means, what was the sample mean in our example? It was coming out to be 2.75, again 2.75, then it came out to be 3.5. But when you have a dice 1, 2, 3, 4, 5, 6, what is the actual mu? It is 3. So you take the difference of the sample means from these expected value, which is mu. Please understand the difference between sample mean and mu. If for all the random variables, that means S1, S2, S3, for all random variables xk, if you sum this difference, xk minus mu, k going from 1 to n, if you sum this difference, of course you need to scale by 1 over under root n, you get a new random variable y. And what is the probability distribution of this random variable? It will be Gaussian distribution with mean 0. Why this mean is 0? We are subtracting the sample mean from the original mean. So the new distribution will have mean 0 and of course variance as sigma square. And what is the shape of this distribution? The shape of this distribution will always be Gaussian distribution. As n increases, it will turn into more and more Gaussian distribution. What is xk? My original distribution was never a Gaussian distribution. I took xk's, that means the samples from the original distribution, which was never a Gaussian distribution, as I showed you in the example. All right. And when I take that distribution, and when I start taking these samples, and I start presenting my samples like this, and it will turn into a new random variable y. The distribution associated with this random variable y will be, as n approaches infinity, will be Gaussian. So that is the power of this central limit theorem. You can take any example. You can model your electronic circuits. You can model your any real-time examples of when you are doing forecasting weather or handling some banking details. You can put it in the form of a Gaussian distribution. But when you look at the original distribution, so they may never be a random. They may never be a Gaussian. So then you get a new random variable. And central limit theorem says that under weak condition, of course, under weak boundary conditions, PDF of y, the probability density function of y, is Gaussian as n approaches infinity, but with mean as 0 and variance as sigma square, because you are subtracting mean here. This is my central. So two important laws I have discussed and tried to intuitively and mathematically try to explain you. One is the law of large numbers, in which the sample mean approaches towards the expected value when n approaches infinity. The second theorem is central limit theorem, that a probability distribution, if you take the random, the probability, how you get the Gaussian distribution when n approaches infinity. So you can model any physical life example or any electronic, for example, in an electronic circuit, there may be many amplifiers, there are other microprocessors, any other. Overall, the current distribution, you can model it as Gaussian. Why you are able to model it as Gaussian? Because the central limit gives us that idea. You take the current flowing through one component, the other component, the third, fourth, fifth component, they may have any other distribution. But when you sum up the distributions and you do it like this, you will end up with a Gaussian distribution. That is why we can model a current distribution or a voltage distribution or a population or a mobile phone call making, right? The signaling in the mobile phone. I mean, there are n number of examples where you can, where the power of central limit theorem is actually used to model your processes. I hope I've been able to explain you the central limit theorem and total law of large numbers, nicely. So if you have any questions, you are always, you're most welcome to ask. Or otherwise, I will end the class. Thank you very much for joining. If you have any questions, you have my phone number, email ID. You can arrange a Zoom meeting with your own Zoom details. Send me the details. I will be there on Zoom. Right. So we can, you can discuss your doubts. No problem. A mutually agreed time we can have, and we can, I can clear the doubts. And it is open for throughout the semester. You can call me anytime, email, whatever. Yeah, I'm always open to connect with you as far as this subject is concerned. Thank you very much for joining.